of the entire IG student chapter, we welcome you, Vino Philip, sir.
Thank you, Nihara. Thank you for this beautiful introduction. Now, sir, just 1 minute. Now, before this session starts, there are some instructions to be followed by the listeners. Microphone should be muted. Camera should be switched off during the entire session. All the doubts and queries can be cleared at the end of the session. You can make use of the chat box or unmute yourself for the same. At the end of the session, please make sure to fill the feedback form since the certificates are initiated based on that. So, the waiting is over. Mr. Vino Philip, sir, the session is all yours.
Thank you. Thank you very much, Pooja. And thank you, Nihara, for the warm welcome and introduction.
Welcome, sir.
I hope you can all hear me clearly.
Yes, sir, you're audible.
You're audible, you know.
Thank you. So, in the interest of bandwidth, I am going to switch off my camera so that I can present my desktop screen for you all to follow the presentation. I would like to, first of all, thank you, Rani, my classmate from CET, and also the HOD, Dr. Narayanan sir, for providing me the opportunity to be with you all to share some of my experiences. Let me try and get my window to work. I hope you can see the presentation. Let's see.
Yes, it's visible. It's visible.
Okay. So I'm going to start with some of the basics of what an FPSO is and how it works. It's mostly a non-civil engineering topic because it's mostly process-driven, mechanical-driven, but there is a section which is involved that is related to marine engineering, which is a close cousin to civil because we do oceanography a little bit. And then there is also the subsea anchoring, the mooring, which is foundation engineering in wet strata in the subsea bed. So that is a more specialized engineering study. I will not be going into too much detail just for the interest of time, and also because I am not the technical expert in these subjects. I'm the project commercial coordinator, commercial manager. So I don't have to be involved in the very, very deep technical aspects of the actual design. What I am going to give you is an overview of an FPSO first. So the second slide, which I'm showing you, is the introduction, the agenda. So first will be the introduction. What is FPSO, EPCI? What does it stand for? Then I will walk you through to a couple of videos, a very short video, FPSO fundamentals video that is taken from one of my previous companies. These are videos available in the public domain in YouTube, so you can always search for them later and find them as well. And the next one is the types of mode FPSOs, which is a video done by my current company, MODEC, which I will share those two slides with videos in them. And then I will explain the mooring options at seabed, just for the fact that this is more related to a geotechnical subject. I will share two of the major mooring options at seabed. Then I will go into a deeper explanation of the cost estimation, the mechanism, the typical project cost estimation progression from early concept selection through FEED, through the actual construction, and then through final as-built. Then I will show you the categorizations of cost items, typical FPSO cost items, what kind of costs are there, the nature of the costs. And then I will explain the cost structures. I have been involved in two companies with FPSOs. One was SBM, single buoy moorings, S single, B for buoy, BOYU, and moorings, M is for moorings, MOORING. Single buoy moorings, which is a Dutch company. And that has one type of cost structure. Then I moved to MODEC. MODEC is Mitsui Offshore Development Engineering Company, MODEC. MODEC. Mitsui is a Japanese conglomerate, like Tata is a huge company in India. Similarly, or Birla is a huge company in India. Similarly, MODEC, Mitsui is a very huge company like Yamaha and, these Mitsubishi. They're a big conglomerate in Japan, but they have international offices. So Mitsui also has their own shipbuilding yard in Japan. So MODEC is Mitsui's. Mitsui is the parent company of MODEC. So I will explain the two cost structures that I have been involved in and the way that I've been working. And then I will explain for the cost estimation, what are the inputs required? Basically, what all coordination activities, what all types of decisions have to be made by the proposal manager, by the execution team, close coordination to ensure that our estimate for our current project that we're expecting to get or sell is properly evaluated and valued, the inputs required, and then the estimation process, and then the approvals at a very high level. So I will walk you through all of those. I am expecting this to be a very high level, kind of a descriptive seminar, webinar. It is not intended to be very mathematical or very deep in terms of designs and things like that. But I will explain a few things, and if you have questions, like Pooja mentioned, please put them in the chat window, or you can note down the slide number. You can note down the question that you have, and we can engage in a discussion at the end. I will give you enough time for a discussion. I'm actually happy if you want to raise questions. I prefer that as a feedback of how well you are understanding the presentation. So first, let me explain the actual abbreviations. FPSO. It's floating. Floating means that it's a vessel. It has a buoyancy, so it can float. And it is moored. Moored means it is stationary. It is anchored to a position. So it's a moored vessel. Production means that it has additional capabilities on the deck. They are designed with additional weight on top of the deck vessel, on the deck of the vessel. So generally, a ship is basically a plain vessel with passenger or maybe container places, and then it's a place for people to stay. That's called the living quarters, LQ. I'll explain that to you. So there's, in addition to the floating part of it, there is also production processing capabilities. Then the cargo tank for storage, that is the S, storage, and offloading is the offloading capacity of the vessel. So we design the hose reel and the pumping capabilities to offload at a certain volume. The important thing is to offload quickly so that the sister vessel that is receiving the product from the stationary storage vessel does not stay too close for too long, because that is actually going to be a safety issue. EPCI stands for Engineering, Procurement, Construction, and Installation. So you're very familiar with it. So we go through all the cost items. So we have to estimate the actual engineering part of it, the procurement part. We have to estimate the construction and the installation. So that is the whole EPCI cost. All right. So this is the video that I'm going to play for you. I hope it works. So let me pause the video as it's going through its cycle, just to be able to provide some context. So this is the floating production vessel. It's a very huge vessel. This is almost the size of 6 or 7 football fields. In India, you play football in the Maidan, grass patch. This length is about 7 to 8 football fields, one after the other. Okay, you will understand that in a moment. It looks small in the context of the ocean. The ocean is so big. So that is the vessel. I'm showing you kind of a feeling of how big the geometry is. The vessel is so small compared to the depth that it is anchored. It is anchored at 2,000 to 2,000 meters depth. And these are the anchor lines that you see, the mooring lines. This is a 3x4. We call this a 3x4 mooring line. So it is anchored at the bottom over here. And these are the mooring lines, these 3 lines over here that you see. 3 over here, and 3 over here, and then 3 over here. So there are 4 directions in which it is anchored at 3 points. So it's 3x4 anchoring. There's a total of 12 mooring lines. In addition to these, you have these yellow lines, which are called the risers. This is where the fluid travels. So this is the subsea layout, just to give you an view. Now you will see kind of like the flow pattern. So like I explained, the mooring line, this is the seabed, this is the actual soil. The sea is above, this plane right above here. And this is the actual well through which the oil is coming. And then from the well, there is a jumper, or it's called a spool or a jumper, to the pipe plect. It's called so this is the PLEM, is the manifold, pipeline end manifold. And this over here, where the pipeline starts, is called the pipeline end termination, the PLET, plect. So they have mechanisms, the piping engineers and the process engineers design mechanisms in here for valve control, pressure control, and everything, so that the flow is properly regulated to the different risers. And then the risers will pick it up, the fluids, and it takes it up to the processing facility. So you see the direction. So this is a very simple processing diagram. It shows only inlet of fluids. There is also inlet, and there is also electronic signals. So there's fluids, there is signals for electronic, that's called umbilical, goes through umbilical cables. And also there is an injector of fluids like water or chemicals. To help the well to flow better, we inject catalysts, admixtures. In civil engineering, you have admixtures for cement, which help the cement to bond properly, to properly bind and to do its chemical processing. In the same way, to get the oil and the fluids to come out of the well, we inject chemicals, and those chemicals prevent the well from clogging up due to some kind of scaling or deposition. And it also helps the flow of the fluid. It helps the viscosity to improve, to bring the fluids up to the processing capabilities. Now the fluids go up through a toroidal swivel. So this particular, I will explain more, is a external turret. A turret is basically a tower. TURRET is a tower. Actually, I think it will show up. So this is a turret and a swivel stack. The swivel stack is a toroidal swivel. A torus, as you may know, is a mechanism that converts linear path of flow through a circular plane into another linear path. So it changes the direction of the linear path of flow. It's not a bend. It's not like an elbow, but it helps to rotate the flow. So there will be a series of toroidal swivels inside this. So each one of these small things you see is a sealed toroidal swivel pack. And there is concentric pipes that are coming through the swivel stack, concentric pipes, one inside the other, and they open into each chamber one by one. So if one pipe opens into one toroidal swivel chamber, from there it will go into the linear path to the FPSO. So this is the technology that the two companies have as patents. SBM has their own, and MODEC has their own. So that way, they have a market competition. But the important thing is how capable are these swivel mechanisms, because you cannot replace them. This is the most critical design in the FPSO. The swivel should not fail during the life of the project. But the moment you have to repair it, it's a very expensive deal. You have to dismantle everything, and you have to plug the wells. You have to stop production, which is so many dollars per day. So there's a lot of cost associated with changing this one critical piece of equipment. So you never want to have any toroidal damage, any toroidal swivel or swivel stack damage. So this swivel stack, once it is installed, it should serve for the full design life. Generally, the design life for many of them is close to 15 years, 15 to 20, 25 years. Okay, so the weather vaning, as we call it, is it allows the bow to wind and weather. So the bow is the front of the ship, the aft is the back, and then there is a stern, port side, starboard and the port side. Bow and stern are the same. And then there's the aft, there's a port and the starboard. So let's see what it does over here. As the wave moves, so as the wind causes the vessel to rotate around the stationary pack. So this is the toroidal swivel that I was talking about. So there's fluids, there is utilities, which is chemicals, there's water injection, and then there is the electrical signals, umbilicals. So that is an FPSO. So I guess this is the flare. The processing is, this is the turret, this is the gas dehydration. So most of the liquids have to go through gas dehydration. Then it goes through separation, which is based out of separation tank, and that is oil, water, gas separation, purely using lowering of the pressure, as the pressure decreases, you reduce the amount of, you can separate the liquids and the gas, and then you take the gas from the top side of the container, the top upper part of the container, and you take the liquids from the lower part of the container. So that's the basic philosophy. So there's the gas, water, and oil. They all come through this processing fluid. After the separation takes place, then there is these turbines power the whole processing facility. In this design, there are 4 turbines. One, you see those chimney stacks? This round thing is the chimney stack. 1, 2, 3, 4. So there are 4 turbines, gas turbines. This is a utility room, like the control room, which has all the electronics and the instrumentation that control all the valves and instrumentations in this vessel. And this is a laydown area, and here also there is a slight laydown area. These are a deck crane. This is a deck crane, this particular thing. So the oil is then processed and it is exported through here. There is also the seawater that we take up seawater for injecting seawater. We take the seawater from the bottom of the ship at little depth, not just at the mouth. We go a little down. We take the seawater in, purify it, process it, remove some of the contaminants, and then it is injected, and the water injection goes through the pipe track, and it comes back into the toroid, and then it goes down to the injection to the well. So water is injected in a purified state, and that water helps the gas and the oil to come up as well. You keep maintaining the pressure of the reservoir below. So this is a very high-level understanding of the mechanical and the process side of it. So the chemical engineer is more the process engineer, and the mechanical engineers design the basic rotating equipment and things like that, and the gas turbines and all that. And the electrical engineer ensures that the electrics work. The instrumentation engineer ensures that the instrumentation works. The marine engineer ensures that the vessel floats. That's the naval architect. And also the marine engineer is involved in the other side of mechanical equipment. There are mechanical equipment below this deck. So you see this deck, there is equipment that is inside the cargo tank for pumping, There is also other marine equipment that is involved in the stabilization of the hydrodynamics of the vessel itself. There's the ballast fluid that helps to maintain buoyancy characteristics of the vessel. There is a certain volume to weight ratio that has to be maintained so that the vessel stays at a flotation height. There is a very important line on all ship-going vessels. That line is the point at which the vessel should not go below or go above. If there is a certain tolerance, if the vessel waterline, there's a waterline level indicator. It's always painted on the vessel. It can also be indicated by two colors of the vessel. That is important to show that the vessel is in a stable condition. Okay, if it goes below that, then it is almost at limiting buoyancy. The buoyancy is not sufficient to keep it floating, and then it could sink. So that's an important characteristic of a line. I forget the name of that particular line. So that is the video first one. Now I want to show you a little bit about the actual mooring system. So this is the different types of moorings. Actually, that went too fast. Let me explain that a little. So this is the mooring support structure called spread mooring. So these lines on the corners of the vessel are the mooring lines. Here it is 1, 2, 3, 4, 5, 6. So this is a 6x4 mooring design configuration. And over here there are 6. Over here there will be 6. And at the back end there will be 6. This assembly that you're seeing here is the assembly for the fluids to come up. So this particular spread mooring concept, the vessel does not turn. It does not weather vane. So there's no rotating. It's called a fixed mooring, and it's a spread mooring. So this is very possible only in the equatorial region, where the flow of water and the wind is very, very, very low. Generally, in the equator, there is not much wind or any things that cause the position of the ship to change or stability to change. So all the fluids can come straight up and into the processing. So you have this whole assembly called the riser porch. This is called the riser porch. Risers are those top things, and the fluid conducting cables or lines. There is a riser. This is the mooring lines, and this is the offloading hose tree. Okay, and this helicopter that you see at the back is where the living quarters is. So every vessel has a place for human habitation, which is called the living quarters. So this is what we saw earlier in the SPM video. That was an external turret. E stands for external turret. So this is another system. In the previous one, we saw that the rotating mechanism was attached to the vessel, right? Over here, the rotating mechanism attached to the tower yoke. So this particular tower yoke, the toroidal swivels are attached to the stationary object. In the other one, the toroidal swivels are attached to the rotating object. And there is the whole balancing mechanism and mooring is done through these ballast arms. So this is also a permanently moored. It cannot detach. The most we are currently, I think MODEC is one of the first companies to design a detachable tower yoke system. We are currently executing that project in Mexico. It's for ENI, is the Italian oil producer, and we are doing it for them. It's called the ENI Mexico project. It's currently being constructed. It will be the first detachable tower yoke. The engineer who's in charge of that is Arun Dugal. He's from IIT Kanpur. He's a civil engineer who then went on to become a marine engineer at IIT Kanpur. And he's the main technology officer designing the detachable tower system. He is responsible for that. Arun Dugal, Duggal. Going on, so here the toroidal swivel is attached to a stationary object called the tower yoke. Now, this tower yoke needs to be rested on the seabed. So this particular concept is very few. It is only required in certain areas because this is at a shallower depth. At 2,000 meters of flotation, you cannot do a tower yoke. The tower will be unstable. So this is possible only in the range of 150 to 600. Maybe 600 is also pushing it to the limits. You can do this concept only in 150 to maybe 300 meters depth. If you want a tower yoke mooring system and a process FPSO. This is an internal turret. The actual hole is inside here, and the hole is called a moon pool. It's called the moon pool because when you look inside, it looks like the moon is shining back at you because of the light. So if the vessel was just floating in the water without the internal turret in place, you'll see a huge hole over here, and you'll see the sloshing of the water inside. And if it's a calm, it looks like a moon from high, a full moon. So that's why it's called a moon pool. The opening is a moon pool. And the internal turret assembly is inserted and put in here. This is one of the more expensive types of turret. All right, go on to. So, like I explained, we have types of mooring systems: the spread mooring system, the external turret, the tower yoke, and the internal turret. All right. Now, I would like to explain a little bit about mooring options at seabed. This may be interesting for geotechnical people. So there are two main types of mooring options at seabed. A torpedo pile. It's called a torpedo pile basically because of the shape and the design. It is intended to be using the launch speed and the launch angle and the depth that it can travel to achieve a certain velocity and then penetrate into the seabed just by the fact that it is guided by these fins. You see these fins, they are like wings of a plane. So these are called torpedo fins, and the torpedo is shaped with a head that is very much almost like a bullet, and it is intended to penetrate by its own sheer speed and weight and the angle that it is launched into the seabed. And it is more expensive to make because it has to be heavier. It has to be created with a lot of weight in it so that it attains a certain velocity so that it can impinge the seabed. Generally, this torpedo piles are useful only in soft seabeds so that you're expecting it to penetrate deep in the ocean floor in a soft, silty, it's a silt. Most of the actual deposits are silt, and it will go in there and get anchored, and then it will not move. So these white lines are depth definitions. They help to define how much penetration has happened once it is inserted in the soil. Whatever you see outside is remaining, shows how much friction is created and how much you can make the judgment of how much friction efficiency you have after it is penetrated the soil. So friction is one of the main things that holds this in place. The other one is called suction pile. The suction pile is just a cylinder, and you have holes at the top of the pile. So this is the top, and the bottom is at the far end is the bottom, the suction pile. And you have to lower this down, and then using pump mechanism. So once it is on the seabed, right, it penetrates because of its own self-weight. It will penetrate to a certain depth. And then after that, to make it penetrate further down, you will put vibration mechanisms on it, hammering mechanisms on it, and you will use suction to displace the water column. So when it goes in, this whole area will be filled with water. So you have to displace the water column and pump the water out as the soil keeps climbing up. Actually, it's not the soil that climbs up. It's more like a straw. You're sucking from out here with you're pulling the water out, and because you're pulling the water out, the weight of the water above it, the head of water above it, will keep pushing this pile further and further into the seabed. So you're creating a difference in the actual head inside the pile versus outside the pile. And because of that, it will keep pushing it further and further into the seabed. And then you can determine at which depth you have reached full friction capacity to prevent it from coming out during mooring. And then the mooring chains attached to the top of these. Okay. So that is the suction pile concept. Now, going into an FPSO. So the next item that I had in my agenda was about so the next item that I had was cost estimation. So I finished the introduction to explain what an FPSO is and the components of an FPSO at a very high level. I'm sure, being a new topic for many people, you'll have questions, but please feel free to ask at the end of the project, at the end of the webinar. Cost estimation. So I'm going to walk you through the typical project cost estimation progression, typical FPSO cost item, cost structures, inputs required, estimation process, and the approvals. Okay. So going back to the typical project cost estimation. So this is a typical project cost estimation cycle from the initial selection and economic study, engineering studies, to basic engineering, to detailed engineering, and then the final construction. And this is the accuracy of the estimate. So this is the actual project cost accuracy, plus 40 minus 30. And we keep funneling down till we come to around minus 10, plus 10 to minus 5% accuracy. Okay, so there is a typo here. It's plus 10 to minus 5. And this is the engineering progress. So this dotted curve that you see here is the engineering definition that takes place, cumulative engineering progress. Initially, you just have a very concept, napkin kind of a design. When you say napkin design, you're referring to somebody sitting down at a table, a coffee table, discussing with a friend, and you're drawing initial sketches of a concept that you have in mind. You're doing it on a tissue paper or a napkin or a scratch paper. So it's basically a very scratch paper design concept, the beginning stages. And then you have to do studies. Then the studies will show whether it's feasible. If it's feasible with major economic considerations, then you go into feed front-end engineering and basic engineering, and then you start creating control estimates. And then you have this final estimate over here, which is used during the detail engineering, procurement, and construction. MODEC as a company is invited by companies like Shell, BP, ONGC, or any other companies. ONGC has also requested our services from Japan. So MODEC has required to provide construction-related estimates because we are more into construction. So our clients are already involved in the project at this stage. When we start coming into the project, we are at this stage. So we are creating estimates in the range of plus 15 to minus 10%. Plus 15 minus 10% we start with, and that is where our contingency estimates and everything are based on. So we start over here, and then we take the project through to construction, commissioning, and final operation. For the FPSO, I'm talking about the FPSO part of it. The actual field development is managed by the client. They develop all the subsea infrastructure. They developed all the other pipelines. They developed even the processing facilities onshore, like the power plant and the hydrocarbon separation and all that. So all those pipeline and terminations collect manifold systems, all that is part of these front-end engineering design concept study. This is a whole project. MODEC and SBM join in at this stage during construction because we are invited to do construction at that point. So the project is going full steam ahead. I just wanted to explain that. That is the nature of our estimation. We are at this point of the project. Moving to the next slide. Now, this is a typical, this is a 2015 cost basis, 2015, so that's about 5 years ago. On the left column, just the serial number. This is taken from a website. You are able to achieve, you can see this as a Compass International. They are a study group that do studies on costing. So description shows you the cost items, typical cost items, major cost items that are defined by the tons. This is the tonnage of the vessel itself. This is including the mooring. So the mooring tons are also in this. And then you have the cost of this is in labor and materials. LNM is labor and materials in US dollars in 2015. And this is the rate, cost of unit rate. And this is the total, which is multiplication by tonnage. And this gives you a proportion of the costs, 100%. Now, this is a study based on 2015 for an average of FPSOs that were done in Africa. Africa and Brazil are the most prolific regions for FPSOs, like I mentioned. They are deep waters in Brazil, offshore Brazil, which is the South Atlantic Ocean, and also offshore Africa, which is also the South Atlantic. There are deep waters with a lot of oil reservoirs, and those places are under a lot of, like in Brazil, Trinidad, Tobago, Guyana, they're all the South American countries which have a lot of offshore oil. On the African side, you have Angola, you have Senegal, you have similar countries on the west coast of Africa, which have a lot of oil blocks in their countries, where most of the FPSOs of the world are there, most of them. It could be spread mode. Spread mode is the cheapest version of FPSO. So I forgot to mention that. Let me just walk through that one important topic I wanted to explain. Let me take you back to the types of FPSOs. The spread mode is the cheapest version of a FPSO because the mooring is very simple. The external turret is also a cheaper version. Between the external turret and the tower yoke, it depends on whether it's a detachable tower yoke. If it's a detachable tower yoke, it will be more expensive than external turret. External turret will be a little cheaper because it doesn't involve as much of the hull ballasting and other modifications. The internal turret will be the most expensive. And amongst all of these, the moment you add a detachable mechanism that the vessel can detach. So spread mooring is always fixed. You cannot detach from the mooring lines and move the vessel away. Whereas all the turret systems, tower yoke, we are doing the first detachable. Till now, all the tower yoke were fixed. Now, MODEC is pioneering a patented design for detaching the tower yoke. And once we detach it, this will also be a detachable system, tower yoke. And the external turret can be a detachable tower yoke system if we have actually no, this is not detachable because the mooring lines are connected at the top, so you cannot detach it. Whereas the internal turret, the actual mooring lines are connected at the bottom of the vessel. So the bottom of the vessel is already inside the water, right? So you can create a transition buoy. A buoy is a flotation device, BOUY. You can create a flotation device below that can be detached from the turret. So the moment you make a detachable turret, you're adding another mechanical component, which makes it expensive, and safety issues and stuff like that. So you have to have, so those are the other cost considerations. The moment it is detachable, it becomes more expensive. And like I said, the spread mooring and the internal turret, these are the cost most expensive is internal thrust. So going back to our current slide of the cost estimate. So this particular model shows you where the different costs are and the different aspects of the cost. So you have hull, then you have the hull is the outer shell of the vessel, and then you have the production system, which is all the mechanical equipment. Then you have the living quarters for human habitation, and then you have certain other equipment packages, which is also part of the production system. Then you have the structural elements on the topside deck, which are basically structural engineering that support all the production equipment. Then you have the storage tanks and their manifolds, which is for part of the offloading system. Then you have anchor chains. This is all the mooring kind of thing. And then you have all the installation from 14 to 14 onwards is the installation, the towing and all those costs that happen during the construction phase. And these are all the labor and engineering management related costs. So this kind of gives you an idea of all the cost elements and aspects that have to go into the typical FPSO cost. So these are the two cost structures I want to explain to you about. The function-based cost system. This is what I used at SBM Offshore. We defined the cost structure based on top size, hull and vessel, which is either a new build hull or a conversion vessel. And then we have the mooring. And we have these three major categories, which is all the labor, all the material, which is meant for the top side, or procured material for marine stuff like offloading and things like that. And also the more material like mooring tails, chains, and everything for the mooring system. And then the services are things like third-party inspections. So in the case of topsides, we have third-party engineering services. In the case of hull, we have third-party certification. So just like a vessel can be considered as a car in the sea. So you have a car when you drive a vehicle or a motorbike or anything on the roads in India or in any country, you have to have its registration certification, right? So it has to be registered that is worthy of using the common facilities. In the same way, the hull is monitored, the vessel itself is monitored by a certification agency, either by ABS, American Bureau of Shipping, or by DNVGL, Deutschland Nordel something. It's a Dutch company, but they're basically certification bodies, and they give you a class certification of your vessel. So that has to be certified. So those kind of services are called class notation and certification. And then you have the mooring services. So you'll have things like ocean studies. You'll have to do seabed study. You'll have to do the sounding studies to see the characteristics of the soil. You have to do soil bed surveys. So those kind of studies are in the services. So those are category-based, function-based cost structures. The category-based structure is what I'm currently using at MODEC. We have defined different cost blocks, we call them, and each of those cost blocks are capturing these costs. So the project management labor is common to all of them. We categorize all of it over here. So in the case of MODEC, MODEC is slightly different from SBM in the way that our companies are structured. MODEC does not do the mooring designs by themselves. MODEC always hires a sister company called SOFEC, SOFEC, to do the mooring system. So as far as MODEC cost structure is concerned, SOFEC is our subcontractor. So we have all the SOFEC costs in the mooring system here separately. We do not capture their engineering costs in our labor. Whereas here in SBM has their own mooring design department, and they're an integrated company. SBM provides everything integrated, whereas MODEC does the mooring as a subcontract service. So everything related to the mooring part, the labor, material, services, everything is in mooring. Whereas the topside and hull is commonly distributed between all these different areas of the cost structure. So labor-related costs are third-party inspections, and labor-related costs are related to the administration of their personnel, travel, taxis, their flights, any business travel. Subcontracted project management services are the third-party inspections. So when equipment is being manufactured at a vendor facility, a factory, we have to go there and do the third-party inspection. We have to send our third parties, MODEC's representatives, to do an audit of the fabrication facility and the factory acceptance testing. So we have to witness all of that. We have documentation to make that happen. So that's all done it's captured in this cost block. And we have project management incidentals, which are related to the facilities that we have to provide to the client, and we have to provide to our own staff at the different locations in the yards. We have to create our own engineering offices. We have to provide desks, IT equipment, and all of those. And that is the project management incidentals. The subcontracted engineering services is related to give me a moment, please. The subcontracted engineering services are related to the topside detail engineering. We hire third parties to do detailed engineering studies for us on the marine side to make sure that the hull, we do the FEA analysis, finite element analysis of all the hull components. We have to do the risk-based evaluation of the hull, which are the most stress points depending on wind and loading conditions. And then we have to do 10-year further inspections of those. So we do a evaluation of the hull strength properties and fatigue analysis of the hull, and that we have to calculate which spots are tender for the vessel body itself, which are the most exposed to fatigue. And those points most likely will be the attachment point for the mooring lines. We have to go there and do further investigations every 10 years to do a continuous evaluation of the vessel to make sure it is seaworthy. And those are risk-based evaluation studies. Then we have other topside design engineering studies, which are done by the subcontracted engineers. That is captured over here. And then we have the classification and certification. Like I mentioned to you earlier, the hull and the vessel has to be classified by by ABS or DNV. So we have to get their certification. We also have local compliance certification. So another important aspect of dealing with international projects is that you are bound by contractual terms. Many of the contracts that are provided to us. So whenever we get a requirement for an FPSO, we are given the invitation to tender along with pro forma we are given a invitation to tender documents along with the pro forma contract. The pro forma contract is a draft contract by which we have to execute the project. In the pro forma contract, there are a whole list of clauses and terms, specifications, and conditions that we have to make. Our costs, we have to recover all the costs to comply with those pro forma contract conditions. So we have to review the pro forma contract. Any qualifications that we need, we have to return the proposal back to the client with all our qualifications. But the local regulations are generally mentioned in the pro forma contract. So in the pro forma contract, we get local regulations provided. So if we're doing work in Brazil or if we're doing work in Africa, especially in many of, even in India, there are some conditions that define what an international provider can do in local jurisdictions. They will say you have to meet a certain amount of local content. It's a very important word because we have to make sure that we cost in our estimates, we add the amount of local content that we have to achieve. If we don't achieve the local content, we have to pay penalty. So that penalty will also have to be costed. In some cases, the local content requirements are very stringent that we cannot meet the local content requirement. So we actually put the cost for the penalty in that, and we add it into the project administration costs will include the penalties. So classification, certification, and all those studies that are required for regulatory compliance are in that file, are in that cost block. Okay. Actually, I just wanted to explain this to you, and I think I have another slide that will help me to go further to that. So after explaining all of this, I will go to the next slide just to make sure that it's a little more time compliant. I think I have almost used up half 1 hour of the presentation. Let me use the next. I have a couple of more slides, but I want to explain a little more about this slide. This is the most important slide that I wanted to share to you in today's presentation. I have purposely put inputs required upside down. The reason is garbage in, garbage out. If the inputs required for a good cost estimate, right, is a good assumption. If your assumptions are not properly coordinated, as a commercial manager, I have to do a lot of coordination and proper checking of everybody's alignment. So if people are defining the organization chart, so this picture over here is the organization chart. This picture over here is the modules execution plan. I will explain the color codes in a bit. This picture over here is the top side schedule, the plan of the schedule. All right. So the major inputs for a good estimate is a good execution plan strategy, how we want to execute the project, and what strength of an organization we need. Who all are we have the project manager, we have the project sponsor above that, then we have the different safety and quality control people and the defined discipline leads. The discipline leads have the discipline organizations which are located in different parts of the world, and under them there are other personnel. So we have to define this organization chart properly, and that organization chart has to be available during these months at different stages of the project at different locations. And this different months and different locations is defined by how we have decided to execute the project, which is based on compliance, local compliance requirements, and the requirements by the client, where they want us to do certain parts of the project. So this is a top-side execution plan document. The different colors mean engineering in a particular house, fabrication in a particular shipyard, or fabrication in a certain processing facility yard, and also the integration in a certain place. So in this project, let's say, for example, green stands for Brazilian local content modules. Each block is a module. So we are considering that all of these modules are fabricated in Brazil, but also we do the engineering in Brazil. So we have to send our engineering team to Brazil from MODEC Singapore, which is our execution center, to supervise them to do that according to our requirements. So we have to issue a request for quotation from Brazil for this. And the gray ones, let's say, are done in China. So we issue these in China. The reason may be because these are considered a little more advanced, and we don't expect the capacity in Brazil to be able to handle the pressure rating and the different risk factors when manufacturing these particular modules. Because they are compression modules or power generation modules, we expect to be a little more complicated and beyond the capabilities and capacity of certain Brazilian engineering companies and fabrication yards. So we define the strategy properly first, and the yellow will be the ones that are done in the shipyard. So the vessel itself, the vessel in this project, let's say, is being done as a conversion. Like I mentioned earlier, there are two types of vessels. There's a new build vessel where we start to create the vessel from scratch. We start from plate cutting, welding, and making a hull first. or we take a conversion. A conversion is where we buy existing tanker. All the time we use a tanker, or most of the time it's a tanker vessel, because the tanker is already designed with oil industry standards. So we buy a older tanker, maybe 10-year-old tanker, which has expectation life of maybe 50 years. So it will be seaworthy for at least another 40 to 50 years. So we buy an oil tanker and then we convert it. So we do that conversion in a conversion yard. So if we do the conversion in a conversion yard, the conversion yard itself has some capabilities for some modules. They can do certain things which are also beneficial to our schedule. So if we do these modules in the conversion yard itself, then we can integrate the other modules around it quickly, instead of waiting for these modules to come from somewhere. So we can make the pipe rack and the flare knockout drum and the workshop and lab and the laydown areas and the deck crane. So these circles are a representation of the deck cranes. So we can install all of that at the shipyard, conversion and repair shipyard, while the hull is being modified for receiving the new topside. And then we can bring the Brazilian modules from Brazil. So the project schedule will have to bring the Brazilian modules over to the shipyard for integration. So we call that the integration process. So we integrate the modules on the deck. And then the Chinese modules are brought from China to the shipyard, which generally is for us in Singapore. And then we integrate it at the shipyard. So that's the whole process of assembling the topsides on a converted vessel. So you have to have these components of a concept properly defined. So you have to have the functional specification from the invitation to tender from the client. The functional specifications will define the design and the technical specifications that we issue to our vendors for the request for quotations, for the commercial quotation invitations to our vendor. Then the project execution plan is what I was explaining in detail earlier about how we define which aspect of the project is performed where. And that project execution plan should be defined based on the conditions that are in the invitation to tender from the client. So we have to read that client document and we have to create the project execution plan by proper coordination and discussion with our execution team. The proposal team talks to the execution team, finds out their capacity of new work that they can do based on the expected milestones for delivery to the client. Then we have to define the project schedule based on that execution plan and within the constraints of where we are doing each component. So some components will take longer in certain areas of the world. Some components can be done quicker because they're more efficient geographical location. So there are possible strikes in Brazil. We expect some kind of mafia activity to take place in Brazil during the execution stages, because it's generally typical that they will not let you offload unless they get a pay raise. So they will stop the offloading of the modules in Brazil, and the labor force will negotiate with their management for a pay raise, and they will stop this. So we expect some delays. So those kind of risks are also costed in, but we have to comply with those risks because there is a requirement to meet local content. So there's a fine balance with how much we want to do in a risky environment and how much we can do quickly in other places of the world. And those kind of risks also we can transfer to the client by proper negotiations and tell them if there are risks, those costs will be considered as additional costs. We qualify those kind of events. Those are force majeure events. But still, our schedule should capture those kind of things so that we are not too far off. Then the organization structure, like I mentioned, is here. We have to have an approved vendor list that the client has also seen and approved, because they have specific products they like to use on their vessels. We have to create our subcontract strategy, like I mentioned, and then the regulatory requirements, local regulatory requirements, which may be defined in the ITT, or which may be just based on the fact that we have to operate in a certain region. We have to get the local approval, and then we have to figure out the handover conditions. So those conditions and the requirement for warranty, how many years of warranty is required for this vessel, and what are the spares that we need. So when we say capital spares, we're talking about major rotating equipment like compressors and also the turbine. The turbine impeller blades are a huge life cycle. We have a reliability and maintenance study, RAM study. A RAM study is called. So the RAM study defines how long the turbine can function at a certain capacity and at what point it is expected to start to have fatigue loads. It's starting to experience fatigue and evidence issues. So when that starts, we have to change out the big bearings and the turbine blades at that point, and we have to put in a new set. And those are considered as capital spares because those spares are very expensive. You cannot claim for those spares later on in the project. You have to claim for it as part of the EPCI cost input. Then we have risk management, like I mentioned, to calculate the contingency required. And then we have the company required overhead, which are indirect costs and the profit margin. So these are the main things that happen when we start to make the inputs required. Once the inputs are received, the project execution plan is received, the local regulations are understood, and we have all these studies in place to understand how much we need to comply with. We create the schedule based on these constraints. So once we have these defined characteristics of the project, we create our schedule, and then we prepare these major working documents, estimation documents. So each section is managed by multiple cost engineers. So each cost engineer has the responsibility to manage the man-hours quantity based on the organization chart and the cost. The cost is defined as the rate with the expected escalation. Then we have the third-party labor, like I mentioned. Then we have equipment and materials, the procurement RFP process. We have to issue the request for quotations. RFP stands for request for quotation. And we have to keep following up during this estimation process, the status, the PSR reports or the procurement status reports, to ensure that we're getting feedback from the vendors with their estimates as per our requirements. And we have to do this for all the areas, the marine equipment, the topside modules, and the EICT, which is electrical, instrumentation, controls, and telecom. So the EICT equipment system. So all of this has to be costed out as equipment and materials. Then we have to cost out the subcontracts. So the subcontracts are the major subcontracts that I mentioned earlier. They are the module fabrication subcontract and the shipyard conversion, repair and conversion subcontract, and the mooring contract. So those are the three major subcontracts, and also the integration subcontract. Those are the major subcontracts that we have to very closely follow. There will be 3 or 4 different subcontracts, one to Brazil, one to China, one to Singapore, for 3 different yards that we are fabricating different components. And also the repair and conversion subcontract involves the shipyard repairing the existing vessel and changing some of they'll have to stiffen the plates. You know, the deck we buy an oil tanker. The deck of the oil tanker is not very strong to support all the weight of the topside modules that are coming on top. So we have to create another plate. We have to create a web of structure, and we have to create a foundation deck that will support the whole topside. So that whole deck has to be refurbished as a foundation to support the modules above it. So that conversion is an expensive project, which is at the shipyard. And also the living quarters. Initially, the vessel had a living quarters which is considered required only for, so the living quarters itself, which is this blue thing here at the edge, this was considered sufficient only for a container cargo, a oil tanker cargo vessel. So they didn't have many staff on it. Now we have to increase the staff. So earlier the staff was maybe 20 staff only on the seafaring vessel. We have to take out the old living quarters and put a new living quarters, which will have to accommodate about 160 to 120 personnel on board. That is the number of people, staffing required on the vessel, on an FPSO vessel, to manage all the components, the marine side and the mooring side and the topside production side. So that's why we have to issue subcontracts to the shipyard to convert the living quarters. The living quarters will also have studies that are associated with it, especially many of the clients would like to reduce the noise levels in the living quarters. So you have to do a noise level study. You have to make sure that you have a certain, what is that called, a certain air circulation, HVAC. So you have to do the HVAC study to make sure that you have air circulation in the living quarters, especially if there's some kind of gas leakage on the topside module. The wind should not affect the gas to come towards the humans. It should stay away, and we should try and prevent any air to come into the living quarters from outside to keep that living quarter place safe. So those kind of studies are all part of the technical studies, HSE, quality conditions, and those kind of services. And then you have the services, the pre-operation, class notation services, the car insurance and P&I costs are part of the administration conditions. P&I is the indemnity insurance, and car is the construction all risk insurance. Then you have the warranty clauses. We have to cost that. So these are all the major items that we need to cost as part of the services. Once we have costed all of this, we have to go through a process of approval. So that is the last slide I have for you today, the approval process and cycle. First, we do the internal approvals. We create a internal cycle. So whenever we get a new proposal that we are required to estimate for the client, we create a proposal bid work schedule, and we have to work towards those timelines. The important idea is to keep those timelines, and it's a plan. You should always have a plan. If you fail to plan, then you plan to fail. So you should always have a plan whenever you execute any project. It's the fundamentals of project management. You should always create a plan and a sequence of what you're planning to do. Once you have that sequence, then you will have more definition of how you can execute your work process. So we create a bid work schedule, which contains all those previous steps, and we define the sequence of what we're going to do. And then we have to come to the final stage of getting approval. So there is the internal approvals, there's the stakeholder reviews and sign-off, and then there's the board of directors approvals. Like I mentioned, an FPSO project can range in the $2 billion to $2.5 billion. It could be much cheaper also, in the range of 1 million, depending on 1 billion, in the range of 1 billion or 1.5 billion. But generally, it's in the range of 2 billion if it's a very expensive project. But the reason that we have to go to board of directors approval is because that kind of an expenditure, the delegation of authority for approving that level of expense always resides with the board of directors. Those are not with the CEO, and the delegation is beyond the limit of the CEO. So the board of directors have to approve it. So finally, it goes to the board of directors for approval. So the internal review cycle, so the board of directors at MODEC meets twice a month, and we have to cycle our approval cycles, because only after that can we send it to the client. So we have to prepare the client submission date, and before the client submission date, we have to choose the board of directors meeting for their approval. And based on that, we work backwards to figure out how quickly we need to create our estimate. So the first cycle is the internal approvals, the cost engineer to the commercial manager. Then the commercial manager works with the cost engineers to finalize any discrepancies or items that need to be changed. And then we take it to our management, which is in my division, the project development management team. Once that is defined, then we go through a risk analysis. We create a risk register that looks after technical risk, that look after market condition risk, that look after currency fluctuation risk for hedging, and any other risk that we think we need to add, like local geographical risk. And then we create a contingency calculation based on a risk analysis formula. We do a probability analysis on each of the cost items based on the risk exposure for those. And then we come to a contingency percentage and calculation. Then with that, we have to get the stakeholder. The stakeholder in any proposal is the execution team, because they are the ones who finally have to execute to the proposal's expectation. So at the beginning itself, like I said, we have close coordination with the execution team to create the project execution plan and the project organization staffing plan and the project schedule. So we have already used some of their input to create our costs and to go to the vendors and collect all the cost items. Once we have assembled it, we have to explain to them how we have arrived at the final cost. They review it, and then they have questions or do not agree with certain things. We have to negotiate and make another additional contingency alignment and risk alignment. And that is what is finally considered as a final proposal for the board approval. And then the board approves it, and then we can issue our commercial proposals to the client. That's how we do a typical FPSO project execution. And with that, I now open the floor to any questions.
Hello. Anyone has any questions to put up?
Hello, am I audible?
Yes,
Yes,
Pooja.
Pooja.
Yeah. So I hope the webinar was useful for everybody. Thank you so much, sir. So is there any queries, doubts regarding the session? Friends, is there
Yeah.
any?
Dr. Narayanan sir has requested, what material is the
Yeah,
toroid made
material.
of?
Yeah.
So Narayan sir, the material is dependent on the hardness study of the particular designer. Normally, it is made up of a high tensile, high hardness steel. The reason for high hardness and high tensile steel is because it has to withstand pressure from the reservoir about 15,000 psi, pounds per square inch. And that material is the one that contains all the vessel, all the pressure when it is going through the fluid pressure. At the same time, it has to be hard enough because it keeps rotating. The toroid keeps rotating, so it has to be very hard, and it has to have good high tensile strength to achieve 15 kpsi pressure rating. The important thing is not really the toroid steel material, also the gasket, the seals. So to enable the actual fluid flow, the seal, the rubber seal gaskets are the most important patent component. That also, the seal also has to behave with the same characteristics as the metal in terms of pressure rating. So it should be able to capture, should be able to sustain up to 15,000 psi. That is the most critical component, the seal, the rubber gasket seal, which is not just rubber, it is a very much polymer-based seal. That is a highly secretive material study. It's a highly patented recipe, very highly patented recipe.
Okay, thank you, sir. Narayan sir, I hope your question was cleared. So anybody else have any doubts or queries?
Yeah,
Anyone else?
I have a
Yeah.
small question. Sir, has there been any major spills that is caused from an FPSO project?
From an FPSO project, there has been one spill recently for MODEC, MV14. We had, it's not a major spill, but it was a spill that created enough environmental evidence. So spill always takes place, but the problem is that since the ocean is so large, you will not see much evidence of that spill happening. The evidence of a spill can be seen by the sheen, the layer of a slight, when you have an oily film on any water surface, you'll see a shine. It will be like a shine, a glaze. It will be like a glossy finish instead of matte finish. So when you see the evidence of a glossy finish on the water surface, there is an evidence of a spill. The major FPSO oil spill was for MV14. If you look up MODEC MV14, you will seen in the news articles about a small spill. The good thing about that spill, at least from my perspective, is that this vessel was not containing much fluid. It had only very residual fluid in it, and the hull cracked because it was a very old single hull. So the hull can be made up of two bodies, two sheets of metal. That's called a double hull system. So you have two plates of steel so the water is outside and the inside is the cargo. So you have two plates of steel. That's called a double hull design. The MV14 was a single hull design, and it had very residual amounts of fluid in it. It didn't have much. It was off work. It was idle, waiting for decommissioning. And just before decommissioning, a small crack appeared and a little bit of the fluid came out. But we were able to manage it and clean up the environment. Thank you, Nehara, for the question.
Thank you, sir. Is there anybody else? I hope there is no other doubts. So is there anybody volunteering for a...
Pooja, 1 minute. Vino,
Yeah.
can I ask what type of material is used for that pile mooring in seabed? What are the investigations you normally do when you conduct a mooring purpose? Geotechnical investigations or something is done? Regarding
So we do the soil study, which involves core sample. We do undisturbed core, and we have a disturbed core sampling. And also we do a penetration test. There are penetration tests that are done to see how much penetration is achieved based on loading conditions. Based on those penetration tests and the core samples, we are able to define how much friction we are able to generate during the actual piling design. So the pile design is based on friction. The final anchor, the resistance, the anchor resistance, the foundation that is required is based on friction.
Okay. Thank you. I hope
Thank you, sir.
Question.
Yes.
Mr. Vino Philip, you have basically been a civil engineer, you studied civil engineering. Can you give an idea regarding your journey from civil engineering to a hardcore, maybe mechanical, that sort of job, the job you are doing now? How you found it in the beginning, how you solved working in a rather new area and things like that? Maybe you can share some of that.
Sure. Yeah. So one of the important things as a student of engineering is that we never stop studying engineering. One of the basic concepts in my personal journey is that I should always keep studying, keep improving and understanding and developing my knowledge of all engineering concepts and understanding. As a civil engineer, we can continue to create our own areas of focus and study, and we move into that area alone. For me, I was fortunate enough to go to Dubai, and I worked in the power industry. I started off in Dubai with a power station. I worked in the power station construction of 2 gas turbines and two steam turbines with boilers. So I was involved in the foundation design, the cable tray, the actual cable, underground cable channel tunnels, and foundation engineering, and also the structural engineering of the top sides of all the actual support structures for the mechanical components. So that started off my initial exposure to the mechanical side of, or the industrial side of the engineering part. So being a civil engineer, I was stuck right in the middle of a mechanical and electrical industrial system, where I was providing the support that those engineers needed. If they wanted to create a foundation, they wanted to create a machine foundation for a vibrating machine, they had to send me the specifications. I had to design the foundation. I had to design the bolting, locations, and issue drawings, foundation drawings, and create the slab depth and all the conditions required to prevent resonance and all those things. So that was my basic fundamental start from structural engineering, foundation engineering, to become a project engineer at a power station. But that power station exposure showed me much of the other aspects, like the processing side, how the fluids from the gas, how the gas is received from the tank, how it is burned in the steam turbine, or how it is burned in the gas turbine, how the waste heat from the gas turbine, it's called the waste heat recovery boiler. That waste heat, instead of being flared out, they take the waste heat, they channel the heat into a recovery boiler. They send the heat into the recovery boiler and they create a steam from the waste heat recovery boiler that creates water, fresh water for the residents in Dubai. So the waste heat recovery boiler sends hot steam into the reverse osmosis unit, and that reverse osmosis unit creates fresh water from seawater for the people of Dubai. So my exposure to being on site at a mechanical industrial location journey to becoming more familiar with processing mechanical industry-based facilities and structures. And then I got involved in drilling engineering when I was in Dubai. I moved to Total, and then from Total I came to Dubai, and I came to US, and I started working in BP. And from BP I joined MODEC, SDM, and then MODEC. But that's been my exposure has been most on the mechanical side of the providing civil-based support to the mechanical industry. That's been my journey so far.
Thank you.
Thank you, sir. The amount of doubts clearly says how interesting you talk. Thank you so much. Is there anybody volunteering for a feedback?
Hey, Vino, this is Roji. Vino, can you hear?
Yes, Roji.
Yeah, how are you?
Good, thank you. Roji is my class.
Yeah, so I don't have any questions because I lost all my civil engineering touch. The only thing probably I get into that, you talk about FEM and also the ships. So I'm just like tuning into to say, like congratulate you on our batch, 92 batch. That's it. Thank you.
Thank you, Roji. Thank you. Appreciate that.
Thank you, Roji, for joining. Naren sir, actually, he is a batchmate from US. He's speaking from US in the early morning.
Yeah, I know. Houston is the center for offshore structures because I have been a bit involved in the design of offshore platforms using American Petroleum Institute codes. I have been a bit involved with that a few years back. So some exposure is there for me regarding that. So Houston is the center of all offshore work.
Yes. Arun Dugal is a very good engineer. He's a good...
Yes.
He's I think Roji can explain your part. You can also join in the talk because it's only our students and HOD is there. So you can join and have an introduction about you itself. Roji, are you hearing it?
Yeah. I'm not working as a civil engineer, but I'm working for a Department of Defense, working for US Navy. Because I completed my master's MTech in structural engineering. Then I moved to US. From there, I took MS in software engineering. So I changed my subject totally. And currently, I'm working as a system analyst for US Navy.
It's a great
Proud
journey.
to have you, sir.
Joining, Roji. Thank you for joining, Roji.
Thank you.
Yes, sir. It's great having a Navy officer here from US. Thank you so much for joining us. So is there anybody volunteering for a feedback session for Vino Philip, sir? Is there anybody?
It was a great... Hi, I'm Akshina. It was a very great program. Hello, sir. It was a very great program, really well organized and plenty of details in each section. Mr. Vino Philip, sir, was a very good speaker. You presented this topic very much effectively. It was a very useful for me. Thank you, sir.
You're welcome.
Thank you, Akshina. So HOD, sir, do you have something to talk about the session? Narayan, sir?
Yeah. Actually, when Professor Rani told me that you're going to talk about FPSO, I told Professor Rani that it's a very, very complicated area for undergraduate students. But listening to the talk, I think you have given in a capsule very, very nicely how the estimation is done. I think this will stand them very good in future years when they move on to higher posts and things like that. It was well presented, very nicely presented, and you made it look very easy also. But we know how complicated it is. Thank you for the nice talk. I think it was well presented. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Our mentors, Rani ma'am, Kannan sir, do you have something to talk about the session? Rani ma'am? Kannan sir? Okay, I hope Rani ma'am has left.
No, I'm not left. I just with the audio. From my actually my close friend of me who was with me for 4 years. We met 2 years back in a alumni meet, and I think Roji. I mean, I didn't meet till now after my BTech. It's a real alumni meet happened in the online here, and really thank for the such a effort in the early morning at 4:30 a.m. It's early there. So for our students, have taken so much effort for presenting a detailed schedule of the details about FPSO and the EPCL project. That's new concept for them, I think. I also got some information about the mooring concepts, and really I was interested to know more about it, and I thought I will ask in detail about it later because it's a geotechnical aspect, so we'll have some discussion on that too. And hope all the students got awareness something that a civil engineer can become to a different area, to an interdisciplinary area also we can work. That's what from the journey of Vino and from the journey of Roji it focuses on. So don't lose hope at any moment. Be a civil engineer, you can do wonders in different areas of your career. So that's what the message which I want to give you with all the students out here. Thank you, Vinu, and I hope Pooja will move on to next part of the session.
Ma'am. Yeah. Any other faculty want to say something?
Any other faculty here? I'm just checking out who is there.
I hope. Let's move on, ma'am.
Kannan is there. I can see that Vin too. That's right.
Kannan sir?
I think he's not there.
No, ma'am. No, ma'am. We don't have him anymore.
I think he left out in between because after that 100 participants, that automatically goes to YouTube. So maybe left out.
We don't have him here. So So on behalf of the whole IGS family, we are presenting a memento for you, sir, for the time, for the more than that, for sharing your information. Thank you so much for that. So we are presenting a small token of appreciation, a small memento from our side. The technical members, can you please show the memento on the screen? Can we have the memento on the screen? Yeah.
Thank
you. Can you see that?
Very much. Yes. Thank you very much.
Yeah.
Thank you. Appreciate that.
Thank you, sir. So, can we have Fatima for the vote of thanks? Fatima?
Good evening, all. Now we have come to an end of this webinar. On behalf of IGS Student Chapter 2020-21, I take the opportunity to propose vote of thanks to Vino Philip sir, who enlightened us with his knowledge and presence. Now, I would like to thank our HOD Dr. Marian sir for joining with us. Now, I would like to give my sincere thanks to our IGS mentors, Rani Miss and Kannan sir, for their constant support to organize this webinar. A special thanks to the organizing committee for their wonderful support and coordination. Our heartfelt thanks to all the students and faculty members of all colleges for their active participation. I would also like to thank all other members present here for making this event a grand success. Thank you and have a nice day.